still try to... Oh, good. Oh, thank you, Avishai. Okay, so we are recording the lecture. So basically what I was saying is live lecture, I'm going to try to break it up into chunks of about 15, 20 minutes, followed by discussion. Okay, so that way I hope those of you who liked the pre-recorded format still, you know, those were the aspects that you really highlighted. And so hopefully between that and recording this, we'll have the same sort of effect. Okay, so here's the plan for today. I'll talk about arithmetic and divide and conquer algorithms. Also today, we'll have an introduction of all the TAs. So what I'll do is I'll start the class. I'll go on for about 15, 20 minutes, and then I'll break for questions. And then by then, I hope all the TAs will be here, and then we'll do introductions. Okay, is that good? Okay, all right. So let me go ahead and share the tablet with you. So let's do a screen share. And okay, so all right, so let's start by talking about multiplication. Okay, so last time where we were, we saw that there was this very interesting algorithm for Fibonacci. You know, so there was on the one hand there was so for computing Fibonacci. Let's see, does this okay, let's see if you can still hear me.
Yeah.
Okay, so last time what we saw were 3 algorithms for Fibonacci: 2 to the n squared, and the time to multiply 2 n-bit numbers. So this time we are going to focus on this problem. How long does it take to multiply n-bit numbers? And okay, so the most naive algorithm that you've probably seen already in, you know, that's the one that you've been doing since grade school, is you take 2 numbers, you multiply them, you know, like this. You do 1 times 17, you do 2 times 17, and you move across by 1, and then you add like that, right? So now there's a different way. If you grew up in Canada or something, there's a different way you might have been taught how to multiply. What you would do is you do 21 times 17, write it in 2 columns. And what you do is you divide the first number by 2 and multiply the second one by 2. So you get 10, 34, 5, 17, 2. Oops, sorry, I was supposed to multiply the second number by 2. So it was 34, 68, 136, 1, 272. And then what you do is you just, you know, we don't like these even numbers, so we just go ahead and cross them out and take the second column and you add it up. So you get 7, 1 carried, 14, 15, 1 carried, 357. Okay, so you could sort of ask, you know, so when we have an algorithm, we always ask, 1, why is it correct? So is it correct? 2, how long? And 3, can you do better? So why are these algorithms correct? You know, it's sort of easy to see, you know, the first one we've been doing since grade school, so we didn't actually ask why it was correct, but but you might think about it a little bit and think why it was correct. Any thoughts about why the second one is correct?
It seems like the first one in disguise.
Yeah, it is the first one in disguise. So let me write it out in a slightly different way, where I write 17 in binary. So it's 17 in binary is one. How many zeros should I put? Is that a right number of zeros? So 1, 2, 4, 8, 16. Yeah, that's 17 base 2. And 21 is 1. Let's see, another 4, right? 1, 0, 1, 0, 1 base 2. Okay, so let's go ahead and multiply these out in binary. So the way you would do it is you would say 1 times this thing. So you'd go 1, 0, 0, 0, 1. Then you would say, well, 0 times this thing doesn't matter. So then, this is, you're doing this again 1 times that. So you'd have 1, 0, 0, 0, 1. Right? So we move over two places because we've moved over 2 places. And then we move over 4 places, and right, and then we add. So it's just like decimal multiplication, except we are doing it in binary. And the answer is, okay. And I take it when you write this out base 2, this is equal to, I hope that's equal to that. Okay. So now, what we want to answer is the question, was this just by chance that this was equal, or was there a real algorithmic reason? So for example, there are certain things that happen by chance, so if you're computing 16 divided by 64, you could sort of say, well, let's cancel out the 6's and we get 1 over 4, and happens to be correct, but only on this input. So when we are saying correct, we mean it's correct on all inputs. And so what you can see is what we did out here when we did this algorithm is we said, well, this was equal to 17. This was 17 doubled twice, so that was 68. And we skipped a row because we did not have a 1 there. And so you can see that essentially this algorithm was just doing binary multiplication. Right? Is that clear? Okay, so now how long does it take? Well, how long do these algorithms take? Well, you have 2 n-bit numbers, and for each of these rows, you're going to be writing out an n-bit number, but shifted over at most n times. So these are going to be at most 2n bits long. And how many of them are there? Well, there are at most n of them. And so you're writing out these n squared entries, and then you're adding them up, right? And so it's sort of easy to see that all this takes order n squared time. Right? And if you want to write out this algorithm sort of formally, here's how you can write it out in terms of pseudocode. So if you're trying to multiply x times y, where y is at least 0, then here's how you do it. If y is 0, you'd obviously return 0. Otherwise, what we are doing is we are saying, well, multiply x by the floor of y over 2, and then return twice the answer, or twice the answer plus x, right? So what this is relying on is the fact that x times y is equal to x times y over 2 times 2 if y is even, and it's x times y over 2 plus times 2 plus x if y is odd. Okay, so but but if you look underneath all this, if you look under the hood, what these algorithms are all doing is the following. So if you write x as x sub n minus 1, 2 to the n minus 1, plus x sub n minus 2, 2 to the n minus 2, plus dot 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 plus x naught, which we can write as summation j equal to 0 to n minus 1, x sub j 2 to the j. Okay. And then if we also write y equal to summation j equal to 0 to n minus 1, y sub j 2 to the j. So then x times y is just summation j equal to 0 to n minus 1 times
Okay. Let's see. Umesh?
Okay, can you hear me?
Yes.
Okay, good. Okay, so where was I? I was just saying, look, here's what's going on behind the scenes, right? If you have an n-bit number, you can write it as this summation of the powers of 2. Similarly, so you write each of the n-bit numbers as a summation of powers of 2. And when you want to multiply, you just get sum over all jk, each going from 0 to n, of
Oh, yeah, it's muted again.
Should we do intros?
Yeah.
Yeah. I'm just gonna share my screen. All right, so I think we'll just go in this order. So I guess I'm first. Hopefully other TAs are here too. Just please unmute yourselves, turn your camera on, and introduce yourselves. So hi, I'm Varun. I'm a senior. I'm going to be head TA this semester. Yeah, I really enjoyed this class when I took it, and I think everyone will have a similar experience. Y'all can reach out to me anytime if y'all think there's any new resources y'all think we should introduce for this online version of the class, and we can work on like getting those implemented. Or any other questions, you can always reach me at varunj@berkeley.edu. Iman is also co-head TA, but he's not here right now. So, and Adnan isn't here, so I guess we'll go to Arun. Is Arun here? Okay, guess not. Okay, Avi?
Hi, sorry, I wasn't able to unmute.
Oh, okay.
I think I just got permission. Hi, I'm Arun. Yeah, I'm a grad student. I'm in charge of writing most of the homeworks and discussions this semester. I also do some research on dynamic programming, which you'll learn about later in the class. So if you want to talk to me about that, I'd love to talk about what people work on in the research level world.
Yeah, Avi.
Yeah. Hey, what's up, everyone? I'm Avi, currently a junior studying EECS. On 170 course staff, I'll be leading recorded content. So all of the recorded discussions and Q&A and hopefully application-based stuff I'll be working on and leading operations for that. And really excited to show like not just theory side of 170, but also how you can apply these concepts to practical things and practical applications of 170 as well. So very excited for this semester. Feel free to hit me up at Avinash J for any questions.
Yeah, just feel free to go ahead like Charles and everyone else. Once
Okay.
before you go.
Hello, everyone. My name is Charles. I'm a third year CS major. I have office hours on Wednesdays from 1 to 2. And also, I'm going to be doing recorded content as well. For me, myself, I like reading, cooking, stuff. I do some RL research. If you're interested in that, just hit me up. And yeah, cool. Hope you have a good semester.
Hey everyone, I'm James. I'm a fourth year EECS major. I am also on recording team with Charles and Avinash. I'm pretty interested in quantum computing, so if you're interested in that, feel free to stop by my office hours or shoot me an email.
Jalen isn't here, so Julius, you can go ahead.
Yeah, I'll go. Hi, my name is Julius. I'm a third year EECS major. I am working on content this semester. I also host a live discussion on Wednesday and an office hour on Monday. Beyond that, I do research in quantum computing, and quantum cryptography specifically. So if you're interested in that, come talk to me as well.
Hello, I'm Kevin, third year in EECS. I'm working on designing content, so discussions and homework, and also recording some of your video walkthroughs. I'm excited to be, I guess, there's a bit of experimentation we can be doing to improve 170 this semester. So looking forward to see what we can create for you.
Okay, hello everyone. My name is also Kevin. Also a third year studying CS. And yeah, I'm from Chicago. I'm doing like a discussion. Yeah, I think that's about it. Yeah.
Manan, you can go ahead. Lily isn't here.
Okay. Hi everyone. My name is Manan, third year CS math or fourth year CS math major. I'm primarily in charge of web related stuff, so uploading videos, managing the website, things like that. And like Julius and Kevin, I'm also teaching live discussion, and I have office hours on Thursdays. Yeah, super into board games. So if you're also into board games, or if you have tabletop simulator or something, hit me up and I'd love to play.
Hi everyone, I'm Ganesh. I taught CS170 last semester, but I'm very excited to teach CS170 this semester. I am working on a mixture of content and pedagogy for 170 this semester. I do have a live discussion later tonight, so definitely stop by my section if you're free.
I'm Nate. I just graduated, so now I'm a master's student. I'm going to be in charge of parts of the project. And yeah, my research is not in theory, but it's kind of similar to theory because I do work on NPR problems, which is interesting. So talk to me about any of that or why nothing makes sense.
Hey everyone, I'm Neil. I'm a fourth year studying computer science. If my office hours are Thursdays 11 to 12. If you ever want to talk about tennis, dance, or anything related to 170, come through or shoot me an email.
Hi guys, I'm Vab. I'm a third year CS major. I love playing tennis and football. Unfortunately, due to COVID, I don't think we can play that right now. But yeah, I'll be working on the project and helping out Nate with that. So yeah, feel free to email me at vabg if you have any questions.
American football or regular football?
Soccer.
Hey, I am Reed. I'm a senior majoring in math and CS. I teach a discussion that is happening a lot later tonight. So come by if you are in a weird time zone or a night owl.
Hi, I'm Noah. I'm a fourth year CS major. I'm a content TA. I'll be in charge of coordinating exams and stuff and also help out with the homework and discussions.
Hi, I'm Varun. I'm a rising senior majoring in CS. 170 was one of my favorite classes. This semester I'll be helping with review sessions and session walkthroughs. I'm also a very outdoorsy person, so if you're into running, biking, or hiking, hit me up.
Hi everyone, I'm Rachel. I'm fourth year CS and Spanish major, and I am working on pedagogy this semester, and I'm also the DSP proxy. So if you have questions about either of those, you can also email me.
Hi everyone, I'm Iman. I'm sorry I'm late. I will be your head TA this semester along with Varun. I have, I've taught CS70. This is my third time. I've taught CS170. This is my third time. I've taught CS70 3 times. I've taught 61C once. I was a group tutor for STAT 134 and a reader for 189 and a TA for 375. So I love TAing, but this semester I will not be having a discussion, but I will be having office hours. And I'm happy to talk to you more about myself in office hours.
Yeah, cool. That's everyone. Thanks for letting us introduce ourselves. And I guess we can go back to lecture.
Okay, great. Let's, thanks everybody. Okay, so let's try again. I'm going to share my screen and let's hope it's better now. I'm now speaking through my, through the phone. So before I start, is this clear enough and can everybody hear me?
Yeah.
Yes. Yeah, is that good? Okay. All right, so let's try this time. Okay, so where we were, we were talking about why multiplication works and why it should be n squared, right? So it works because, hidden behind any of these algorithms we have seen, all we are doing is we are taking all the bits of x and multiplying it by all the bits of y, shifted by the right amount. So that's the beauty of the positional number system. And it looks like there are n bits of x, n bits of y. We want to multiply each bit by each other bit, n squared, right? So it's clearly an n squared algorithm, right? So what we're going to do today is we are going to learn about an algorithm that is better. So this is called, is it Karatsuba algorithm? And it's going to be our introduction to divide and conquer. So what do we do in divide and conquer? So we're given a big problem to solve. So we're given some big problem to solve. The first thing we do is we break it up into pieces. We might break it up into 2 pieces or more pieces, right? So let's go ahead and break it up into some number of pieces. Okay, and then the next thing we do is we solve each of these pieces recursively. So that requires no thought at all. We are just calling up our program recursively, okay? So we solve pieces recursively. Third thing we do is then we take all these solutions and we glue them back together to get a solution to the original problem. And then the last thing we do is, or maybe the 0th thing we do, so maybe that's the thing I should have said in the beginning. If the problem is very small, then we just solve it by brute force. Okay, so if it's a constant size problem, it'll take us constant time to solve. We just solve it. Okay, so what, it's an interesting this is an interesting attack. And the things that we have to think about when we actually try to figure out how to design a divide and conquer algorithm, this, of course, is easy. That's really easy. Brute force on small instances is easy. Okay. Solving the pieces recursively, we have to do nothing in order to solve the pieces recursively. They are smaller pieces. The algorithm will take care of itself. So the only pieces that we really have to worry about are, only parts of this algorithm are how do we break the instance into smaller pieces, and how do we glue the solutions of the small pieces together to get a solution for the whole problem. That's where the entire work goes in. Okay, so let's see how to do multiplication by divide and conquer. So let's write out x as, here's what x looks like. It's an n-bit number. But now we are going to break it into two pieces. So they're going to be the first n/2 pieces, which we'll call x left, and the last n/2 pieces, x right. So that's n/2, and that is n/2. Now, in everything that follows, I'm just going to assume, when I'm dividing n by 2, n must be even. So in fact, often when we are doing divide and conquer, we'll even assume n is a power of 2. Right? Or 3 if we are breaking into 3 pieces, And this is not going to cause any trouble for us. So for example, if we started off with any n, then we have to at most double n before we get to a power of 2. And it doesn't matter. We can just take our number and put zeros, leading zeros, and make it into a power of 2, the number of bits. Okay, so now we also take y, we divide it as y left, y r. Okay, so that's what it looks like visually. Let's now express x as in terms of x left and x right. So x is just going to be 2 to the n/2 times x left plus x right. And y is going to be 2 to the n/2 times y left plus y right. So now if you want to compute x times y, it's just 2 to the n/2 x left, 2 to the n/2 y left plus y right. And if you multiply it all out, we'd get 2 to the n xl xr plus 2 to the n/2 xl yr plus xr yl plus xr yr.
Which I think
So,
the first term is XLYL, right?
I'm sorry?
The first term is XLYL, I think.
Oh, right. Good point. Thank you. Right. Good. So that was this times that. That gave us a 2 to the n. Okay, so now let's see how we've broken up the problem. So we've broken up our problem into, if we could only multiply this, 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 and that. Right? So we have 4 multiplications, each of which involves n/2-bit numbers. And then there are these additions, and then there are multiplications by 2 to the n/2. Well, multiplication by 2 to the n/2 is very easy. It's just shifting left by n/2 steps. So the additions are linear time. So if we were to say, let t of n be the time required to solve the problem on n-bit numbers, to multiply 2 n-bit numbers, then we get that the amount of time we need is, we need to solve 4 instances of size n over 2, 4 times t of n over 2, plus everything else we have to do is additions and shift left, so that takes order n steps. So now we are, so how do we figure out how long does this take? Well, obviously when n becomes very small and when n gets to constant size, then we can do these multiplications in constant time. So if we are starting with an instance of size n, then we get 4 instances of size n over 2, 16 instances of size n over 4, and so on. Okay. So first question, how many levels will these recursions take us? So each time they're going from some number of bits to half the number of bits, right? So this tree is going to have depth log n. And then the question is, how many leaves does it have? Well, the number of leaves it has is, we get 4 at the first level, 4 squared at the next level, 4 cubed at the next level. So the number of leaves is going to be 4 to the power of log n. Here, log n is to the base 2. Right? Okay, so so this is, if you want to see how, there are many ways to write this down. One way to say it is, this is 2 to the log n times 2 to the log n, because it's 2 times 2 whole raised to the power of log n, and 2 to the log n is n, so you just get n squared, right? Another way to do this is to say, well, 4 to the log to the base 2 of n is the same thing as 2 to oops. Okay, sorry. Okay, so there are various ways of doing this. Maybe I'll wait for questions and then I'll show you in more detail how one deals with this sort of thing. My main point here is, right now we have a divide and conquer algorithm, but we did no better than what we started with. It's still n squared time. Okay, another way of saying this is, this was an algorithm where we divided, but we didn't really conquer so well. Okay. So it turns out that there's a way to get around this, but maybe before I do that, let me open up for a few questions and see if there are any questions. So
you can unmute yourself if you want to ask a question.
Hi, Professor.
Yes.
I was wondering why we are having the big O of n.
Where did you? Oh, why is there a big O of n here?
Yeah.
Okay. So remember what we are doing. We want to multiply x times y. And what we said was, the way we'll do this is, we are going to recursively multiply xl times yl, xl times yr, xr times yl, and xr times yr. These are n over 2 by n over 2 multiplications. So this is our 4 times t of n over 2. Once we have these numbers, we are going to have to add them. We're also going to have to shift some of these numbers, multiply them by 2 to the n over 2, which means that what we are doing is taking these numbers and shifting them left by n over 2 places. Each of these operations requires order n time. Right, so in addition to doing the recursive calls, which take us 4 times t of n over 2 time, we also have to do order n extra work to clean up. Okay, so going back to our basic philosophy of divide and conquer, what it says was, well, we break into pieces, we solve the pieces recursively. So we broke into pieces by breaking x and y like this, right? Then we solve the problem recursively by saying, do these computations recursively, right? Then we have to glue all the solutions back together. So how do we glue them together? Well, we have to follow this formula. This allows us to glue these solutions back together. And that gluing process takes us order n time. Is this clear?
Okay. Thank you.
Any more questions?
Also, how is number leaves equal to 4 to the log n?
Okay, so look, there are 2 different things going on here. So there are two different important things going on here. So let me write the 2 things down here. Okay, so in each recursive call, in each level of this divide and conquer, what's happening? N is being mapped to n over 2. Oh, sorry, n is being mapped to n over 2, right? The other thing that's happening is the number of pieces we created from one piece is, so one piece, okay, so let me just say what we created is 4 subproblems, right? So we started with 1 problem and we created 4 subproblems, 4 pieces, right? So there are 2 different parameters associated with this divide and conquer algorithm. One is how much we drove down n, so we halved it at each step. The other is how many new pieces we created. Okay, so how much did we drive down n? Well, we halved n at each step. So that's going to determine the depth of the tree, right? Because we went from n to n over 2 to n over 4. How many times do you have to divide n by 2 before you get down to 1? Well, that's log n, right, by definition. So that's why the depth of the tree is just log n to the base 2. Okay. Then we want to know how many pieces did we create altogether? So we went from 1 to 4 to 16 to 64 to, we just keep increasing the number of pieces exponentially as we go down. So how many did we create? Well, the number of leaves is going to be 4 to the power of the number of levels of recursion. So it's 4 to the log n, right? And that turns out to be n squared. Okay, so it's how these 2 parameters play with each other. How quickly you're reducing n determines the depth of the tree. How quickly you're proliferating now subproblems tells you how many you end up with at the last step. Okay, so these are the key parameters, and we'll see changing them only by a little bit is going to change the amount of time that our divide and conquer algorithm takes by a lot. Okay.
Thank you.
Yeah, good, great, good question. So, any other questions?
I have a question. Yeah, sorry.
Yeah.
To quickly clarify, it seems like over here, it's not the depth or the branching factor individually that determines the total runtime. Rather, it's the total number of leaves, correct?
Yeah, so you see, here's what's happening. So when you're doing this divide and conquer, you have to add up the amount of work you do at each level of the recursion. So at the first level, you're taking order n time, right? As you go down the tree, if you follow it out, you're actually going to be taking more and more time. And because the tree grows, geometrically, exponentially, right? You end up getting a geometric series. So the largest amount of time is taken in this case by the leaves. And in fact, once you account for how much time is taken by the leaves, all the other levels, if you add them together, that's no more time than it takes you to do all the leaves. So the total running time of the algorithm is dominated by the leaf. And we'll see that this is a general phenomenon. You know, when we do divide and conquer, in very general conditions, either it's the leaves that are going to dominate, or it's the first step that's going to dominate, right? More or less, you know. So either this tree is going to get, you know, the amount of time is going to keep shrinking, even though you have more and more pieces. Each piece takes you so much less time that the total time shrinks down. So your algorithm is dominated by the first step, you know, whatever it took you to solve this first level. Or more often what's going to happen is that this tree grows very quickly, and then down at the leaves, each leaf takes you only a unit amount of time because it's a constant size problem. But the number of leaves is so large that that's where the running time of the algorithm comes from. So that'll be the typical case. And this is, you know, in this case, it's a typical case. You know, the number of leaves is very large, it's n squared. Each takes constant time, so the running time is n squared.
Professor?
Yes.
I have a question regarding the ON time of the first node. Yeah, the first nodes we are dividing the problem into 4 subparts.
Mm-hmm.
Like, is it because we are adding all these 4 terms together, it becomes ON time at the very top level? It's like this XL and YL eventually becomes like an n-bit number because they're getting shifted by 2n. So it becomes, you know, 4 n-bit numbers.
So, you know, all these numbers, so XL times YL is an n-bit number. 2 to the n times XL times YL is a 2n-bit number. So each of these numbers is somewhere between n and 2n bits long, and you're adding them, you know, that takes you order n steps, maybe 2n or 4n or whatever it is, right? Yeah. So in fact, let's do one other calculation just to make sure that everybody is on the same page. Suppose that the first level, the total amount of work done here was C times n. Okay. This is the amount of work done to glue the pieces back together, right? So now, what's the total amount of work that's done at the second level? Okay, so what you know, we have 4 sub-problems that we are going to be solving, right? So for each of them, we'll be doing gluing, but now the size of the problem is only n over 2, right? So each of these is going to take C times n over 2 steps to glue back together, right? But then remember, there's not one of them, there's 4 of them. So the total amount of time we'll take here is 4 times C times n over 2. So it's 2 times C times n. Okay? And if you go down one more level, now you'll get twice as large again. So you'll get 4 times C times n. And you keep going, you know, you keep doubling at each level. So you'd go n, 2n, 4n, 8n, and so on. And you keep going log n times, and the lowest level will be n squared. Okay, so that's how you're getting the n squared. Does that make sense?
Professor?
Yes.
Can you explain once more time, like, why you have to multiply by 4 again? Sorry, I didn't quite get that part.
Okay. So remember, up here at the leaf, at the root, we had only one problem we started with, but the problem was of size n. Multiply these 2 n-bit numbers with each other, right? Okay. So now we broke it up into 4 parts. What were these 4 pieces? This piece was, please multiply x sub l with y sub l, right? That's what we were telling this algorithm, right? So x sub l and y sub l are each n over 2-bit numbers, right? And similarly, this one said, multiply x sub l times y sub r, and so on. Okay, now out here, we said the amount of time it takes us to take these 4 solutions and glue them back together, which is what this was. This was a gluing process. This was some constant times n. So I'm putting the constant explicitly, C times n. Okay, so now we go back to this problem, right? When we solved this, we broke it up into 4 parts itself. And then when we got back the solutions, we glued them back together. So how long did it take us to glue them back together? Well, if it took us c times n steps to glue these 4 pieces back together, when we are here, we get pieces which are half as large, so we take c times n over 2 time to glue them back together. Okay? But now remember, we have to do this not only for this, but we had 4 such problems, right? We had 4 such multiplications we had to do. For each of them, we had to do the gluing after we got back the sub-problems. Each of those gluings took us c times n over 2 steps. So when we account for the fact that we have to do this 4 times, it takes us 4 times c times n over 2 times, right? Which is 2 times cn, which is twice as much time as it took us altogether on the top node. So as we go down from the levels of the tree, the amount of time we are spending, the time we are spending per node is half as much, but the number of nodes is 4 times as much, right? So the net effect is the total time we are taking is twice as much, right? So we go from n, 2n, 4n, 8n, and we're going down log n levels. So by the time we get down to the log nth level, we are taking n squared steps. And that's the dominant term for the running time of the algorithm. Okay, and it's a geometric series, as you can see. So it's going to be dominated by that biggest term. That's what the running time is dominated by.
Thank you.
Sure. Great questions, by the way. Any other questions? I'm happy to go as slowly as you want. It's more important that you get this right. If you get this right first time, then you'll have it for life. So,
Professor,
yeah.
I was still just a little bit confused on if there's n leaves, right? And then for each of the leaves, for example, you need to do O of n work. That makes sense to me that at the bottom level, it should be n squared. But also, don't you have to go all the way back up the tree? And besides the leaves, there's a lot of other nodes that you need to again do O of n work.
Okay. So let me try to correct something before we go on. They're not n leaves; they are n squared leaves. Okay. For each of the leaves, you do only a constant amount of work, right? So it's a tree of depth log n, but it's not a binary tree. Right? There are 4, it has a branching factor of 4, not of 2. So when you have a branching factor of 4 and it's a depth log n tree, you'll get n squared leaves. Okay? So remember what we are doing. We are, the work we are talking about is work that you have to do as you go up, right? So what I'm saying is, look, as you get these solutions and you start gluing them together, that's what you mean by going up the tree, right? You get back your recursive call, your recursive call comes back, and now you're piecing you take these small solutions and you want to piece them together. That takes work, absolutely right. That's what we were figuring out here. That was c times n at this top level. That was 2c times n at the second level, and so on. Okay, so it's n, 2n, 4n, and so on. At the bottommost level, the amount of work you're doing is n squared, right? So you do have to do all the work at the top of the tree as well, but it's small compared to the amount of work you're doing at the bottom of the tree. So if you want to know what's the total running time, well, yes, there's work you're doing near the top of the tree, but that's small. We don't care about it. In big O notation, essentially all the work is being done near the bottom, right? The total work being done is twice as much as what's being done at the leaves, right? So in big O notation, it all gets swept away.
That makes sense. Thank you.
Does this make sense? Yeah, okay. More questions?
Professor, I don't clearly understand how come the gluing process takes the big O of n time. Like you said, shifting and being multiplied by 2 to the n over 2 and all that. So like, how does that all become big O of n while gluing?
Well, Yeah, so I'm assuming that you can shift numbers in linear time, right? So you have an n-bit number, you just want to shift it left by n positions. I'm assuming that that's something that's given to us. If you want to just shift those bits left by n positions, that it should take you only n time, right? You just have a wire which takes you from here to there, right? That's a unit step, and so you have to shift over not one bit but n bits. So it's n time. Okay.
So because 2 to the n takes the most time while gluing, that's why it's big O of n, because it takes linear time to shift, which is
It takes linear time to shift. It also takes linear time to add numbers. Okay. Any other questions?
Hi, Professor. I'm not sure if you can hear me.
Yes, go ahead.
So, the number of leaves is like n squared. Does the leaves take O1 runtime? So that's why the whole runtime of this algorithm is n squared?
Yes.
Okay. Thank you, Professor.
Sure. Okay, so now let's go ahead and look at a different algorithm which does much better. So this, Karatsuba's algorithm is based on a trick, and it's a trick that actually was, it's the same trick that the famous mathematician Gauss came up with when he was in grade school, or was it high school? I think it was grade school. Okay, so what was the trick? How do you multiply complex numbers? Okay, so if you're given two complex, so this is Gauss. Okay, he was a great mathematician in the, was it 19th century? I believe. Okay, so how does this work? So suppose you're trying to multiply two complex numbers. So remember, complex numbers, square root of -1 is denoted by I, so the imaginary number I. And then suppose you're given two numbers, A plus BI, so that's a complex number, C plus DI. And you want to multiply these together. So what's the product? Well, it's A times C, and then B times plus B times D times I squared plus A D plus BC times I. And now remember, I squared is -1, so it's just AC minus BD plus AD plus BC times I. Okay. So clearly, if you want to multiply two complex numbers, you need to do 4 multiplications. So here was Gauss's trick for multiplying two complex numbers. So he said, look, here's a trick. What you can do is you can multiply A plus B times C plus D. Okay, so what do you get? Well, you get AC plus BD plus AD plus BC. Okay. So look, this is exactly what we wanted here. So now we can get this answer we were looking for with just 3 multiplications and some number of additions. So what we do is we compute A times C, B times D, and we also compute A plus B times C plus D. Okay. So we've computed A times C, B times D, so we have both of these. And now if we just compute A plus B times C plus D, whatever this was, minus AC minus BD, then we just get AD plus BC, which is this thing. Okay, so we managed to reduce the number of multiplications from 4 to 3, at the expense of doing two additions and two subtractions. Now, algorithmically, subtractions are just as costly as additions. So this is like 1, 2, 3, 4 additions. So what we did was, instead of 4 multiplications, we have 3 multiplications and 4 additions. Okay. So let's see what this does for us in terms of multiplication. So what it does is, we want to compute 2 to the n over 2 xl plus xr times 2 to the n over 2 yl plus yr. Right? Remember, this was 2 to the n xl times yl plus 2 to the n over 2 times xl yr plus yl xr plus xr yr. Okay. So now, see, this is the sort of thing we want. Okay. So let's just compute xl plus xr times yl plus yr. So this is xl yl plus xr yr plus xl yr plus yl xr. Okay? This is equal to that piece up above. Okay? So now, if we were to compute this product, and that product, these 3 products, from this, we can find the sum of these 2 products. Is this clear? Right. So to multiply x times y, which are 2 n-bit numbers, what we're going to do is multiply xl times yl, that's 2 n over 2 bit numbers, xr times yr, 2 n over 2 bit numbers, and then xl plus xr times yl plus yr. Okay, again, essentially 2 n over 2 bit numbers. So what we now have is t of n is 3 t of n over 2. And again, the rest of the stuff we have to do is shift left by n positions or n over 2 positions, and then do these additions and subtractions. Actually, yeah. Okay, so still big O of n steps. So now, what does this do to the running time of our algorithm? So remember, there were 2 things that determine the running time of our algorithm when we do divide and conquer. So let's see what those look like. So n still goes to n over 2, right? But the number of pieces we are breaking the problem into is we are creating 3 subproblems instead of 4. Now you might think, well, we just went from 4 to 3, nice trait, but how useful can it be? The point is that when we are using it inside divide and conquer, inside something that's called recursively, it matters a lot. And you can see why it matters a lot in terms of, okay, so again, we start with a problem of size n. We go to n over 2, but only 3 subproblems. And then each of these, we get 3 subproblems of size n over 4, and so on. We just keep going down. How many levels of the tree do we get? We just get log n levels of the tree. But now, the branching factor is only 3. And so the total number of leaves ends up being 2 to the power of, oops, n to the power. So it's going to be, it's going to be 3 raised to power log n to the base 2. Okay, and this, it turns out, is the same as n raised to power log to the base 2 of 3, which is like 1.7 something. Is it 1.732, something like that? 1.7 something, 1.71 something. Okay, so here's a, it's pretty remarkable. So here's an algorithm that works better than n squared time. And it gives you a way of multiplying 2 n-bit numbers. Okay, so you might sort of ask, well, what happened to this intuition I spoke about right in the beginning? And I said, when you're multiplying 2 n-bit numbers, you essentially, this is what you're doing. You're writing out each n-bit number as in binary. And you have to multiply every binary, every bit by every other bit. So there are n squared, n possibilities here, n possibilities there. So n squared combinations, and you multiply them together. So it takes you n squared time. So what was wrong with that intuition? And how is it that Karasuva's algorithm does better than that? Right? And that's where, these properties of addition and multiplication come in. Right? The fact that if you first add and then multiply, then you're multiplying all those things together in one go, right? That's what's happening here. You're taking XL plus XR times YL plus YR, and you're getting 4 multiplications in one. Now, of course, these are not the 4 multiplications we wanted, but we can take away the 2 products that we did not want, and still get left with the 2 products we wanted, because we didn't want XL times YR and YL times XR separately. We just wanted their sum. And so that's where the savings comes from. Okay. Let me, okay, so let me just say that, what we've been looking at in terms of how these, how these recurrence relations work in terms of, how do you figure out running time? There's this standard way, there's just a theorem that you can apply, which keeps track of what happens when you have, when you have a branching factor of A, and n goes to n divided by b, right? And the total amount of work you're doing at this level is n to the d. That's the amount of work you have to do to glue the subproblems together. So these are the 3 parameters that we have to talk about when we are doing divide and conquer. So, of course, nobody says that the work has to be a polynomial of the form n to the d. So there are even more general formulas that we can look at. But this is a pretty good formula. And, for most cases, for many cases you'll encounter, this is going to be enough for our purposes. And basically what this theorem says is that there are 3 cases, right? The first case is when, as you look at this, this tree and you look at the number of leaves, well, it turns out that the amount of work you're doing at this first level, that dominates. And so T of n is going to be dominated by this very first term, order n to the d. So that's the first case. And that happens when there's a condition, when d is greater than log of a to the base b. there's the second case where the number of leaves is very large. You know, the kind of case that we saw. It's much larger than the amount of work you're doing at the top level. When that happens, it's always of the form n to the power of log of a to the base b. So in Karatsuba's algorithm, we had a was equal to 3. So we had a branching factor of 3. And n was going to n over 2, right? N was being mapped to n over 2. So b was equal to 2. And so we got order n to the power of log of 3 to the base 2. And then there's a third case when it so happens that these two factors just completely, you know, it's completely hanging by the edge, where the amount of work that you do at this first level is exactly equal to the amount of work that you're doing at the second level, and so on, all the way down to the leaves. In this case, the number of, you know, the height of the tree is only log n, and so the amount of time that you're going to spend is n to the d times log n. Okay, so these are the three cases that you'd get depending upon, you know, how these three parameters relate to each other. A and B, which is the branching factor versus how much you're reducing the size by, and D, which is n to the d, how much time you're spending gluing the solutions together. Okay. Okay, so any questions? While you're thinking of questions, let me just tell you how we are going to think about, you know, just remind you about how one does logs, right? So how do you think about logs? So remember, if a to the power of k equal to n, then k equal to log of n to the base a, right? Remember that? So that's just the definition of log. Now suppose that a to the k equal to b to the l equal to n, right? So now k equal to log of a to the base n, and l equal to log to the base b of n. And now if you want to relate so what do I want to say? I want to actually say, okay, so so I want to relate k to l. So oh my goodness. Sorry, I should have, you know, I'm too used to just doing it, and now, does anybody have any advice, or should I still ponder it?
Maybe you can write log n for log a.
I'm sorry?
K is log n over log a, L is log n over log b. No, maybe.
K is log n over log, right. So that's what I wanted to get. Yeah, no, but that's what I wanted to derive. So why? Okay, but let me just say that it's log n divided by log a, and L equal to log n over log b. So I want to say, therefore, K over L is log b over log a, which is log b to the base a. Right. So okay, but sorry, this is not helping you, because what I wanted to do was derive all this from first principles, but I'm just telling you how it's done rather than So okay, sorry, I'm missing the. Okay, so there's this should okay. So let me just say, instead of telling you how it's done, let me just tell you that there's there's a way that you can just do this from first principles. You can derive all these things, and if you take the shortest path through, it's really extremely simple. But then once you know it, then you sort of just remember it and you do it. I'll just post a note about it later or something. That
Professor.
Okay.
There was
Yes.
a question by Move.
Yeah, I have a question. So at the end of this, we got the algorithm for n to the power 1.7 or something. But like, is there a case or like some equation that says that, oh, the best we can do during multiplication is like some other algorithm, which could be like better? Like, we don't know the algorithm for it, but this is the final.
Yeah. So very good question. No, that's a very good question. So the point of Kartsuba's algorithm is that it gets us beyond the the magic n squared bound, right? It seemed like n squared was the best we could do, for a very good reason. And this says, no, you can do better, and you can do better because you don't need to, this intuition you need all these products was not true, because you just needed the sum of some of these products. And it turns out that if you follow this further, you can get an almost linear time algorithm. Okay, so you can get something which takes n times log n times log n steps, something like that. And in fact, that's based on the fast Fourier transform, which is something we'll get to in a lecture or two. Okay, so it's actually you can actually go from n to the log 3 to almost linear time. Okay, and that's really surprising. It's really quite remarkable that you can do that. More questions? Can I ask a question? Is the sound quality acceptable or is it good?
I think it was.
Good. I'm sorry?
Was a bit better earlier, but it's good. I mean,
it's good. Okay. So this is it's an acceptable solution for okay, great. Well, that's good. Any other question?
I'm still confused why if b is equal to log ba at this time tn is equal to big O n to the d log n.
I'm sorry. So you're confused about this theorem, right? Is that correct?
Yeah. Why if d is equal to log ba? I just.
Okay. So you're saying you're confused about this middle case. Why is this the case? Right?
Yeah,
is that what you're asking?
Yes.
Okay. Well, so let me say a little bit, and then so by the way, this is this theorem and its proof is being covered this week in discussion. So in the discussion video, it's being discussed at great length. So that's why in the lecture, I only covered it very, only at a high level. So basically, here's the picture. The picture is, look, this is going to be a tree, right? It's a tree that that spreads out, and eventually at the base there are lots and lots of leaves. But each node in this tree has some takes some processing. So at the top level, this node takes how much time does it take? Well, it takes n to the d time to just put all these pieces together. Then at the next level, how much time does it take? Well, n is now replaced by n divided by b. So it takes you n divided by b raised to the power d amount of steps to deal with one of these problems. But now remember, there's not one problem, there are a such problems that you're solving. So the total time it will take you is a times n over b to the d, right?
Yeah.
And then at the next level, it'll take you a squared times n over b squared to the power of d, right? Because now instead of n over b, or each problem will be of size n over b squared, and then each of them takes n over b squared to the d amount of time to solve, and then there are a squared of these, right? Each gluing takes this time, and there are so many problems to solve, and so this keeps going on. This is a geometric series.
Oh.
Okay.
I see.
Okay. And now there are three cases. Either this geometric series diverges, meaning that the term right at the bottom, a to the k n over b to the k whole to the power of d, where k is whatever log n, right? That this is the biggest term. Then then that's what the solution is going to look like. That's if you work out what k is and substitute, you'll get this number. The other possibility is that this series is converging, meaning it's getting smaller and smaller as you go down, in which case this first term is the biggest term. And then the third possibility is you have it just right, so where this term is equal to this term, equal to this term, and so on, right? So in this case, each of them is equal to n to the d, but how many of them are there? Well, there are log n levels to the tree, so it takes you n to the d times log n. So those are the three cases in this theorem, right? So when you look at the details, you actually work out, well, what is this geometric? Obviously this is geometric, but then you have to substitute k, and you work through the calculations, and then you get these, right? But you can already see that this is the form that it must have. Okay.
Thanks.
Right. Any more questions? Oh, sorry. I should have mentioned something during lecture. So here's how I'm going to be doing my office hours. So during the weeks that I have lecture, I'll do a half-hour office hour after each lecture, right? So I'm going to stay here till 5:30 to answer any questions anybody has. I think that's that's just, hopefully it's going to be more efficient for you, and this way, we'll get many more people participating and many more questions. And then if you have some, something else important to discuss, you can also email me and we can set up an appointment, right? So that's the way I'll handle my office hours. So, okay. So, you shouldn't feel like we are rushed. We can take our time. We still have till 5:30.
Professor?
Yes.
So I had a question pertaining to the master theorem. I suppose what I was kind of confused about is what is the big idea of this theorem? What exactly what are these equations pertain to in particular?
Okay, so let me just go back a little bit, and then let me just orient you to where we came from. So we came from here, right, where we said, look, there are these two very important parameters. One is, how did we break? When we broke up the problem into subproblems, how much did n decrease? So here we are saying, well, n decreased by a factor of 2, right?
Yeah.
So instead of problems of size n, now we have problems of size n over 2. There was a second parameter that was very important, which was how many subproblems did we have? So in this case, it was 3. And the fact it was 3 versus 4 was very, very important in determining what the total time was. And then there's a third parameter which we didn't talk about, which is how much time does it take to glue all these pieces together? So for us, in the two examples we saw, it took order n time. That's n raised to the power of 1, right?
Yep.
So there are 3 parameters. How much we decrease n by, this factor of 2. How many subproblems? This is the factor of 3. How much time did it take? So that was n to the power of 1. And then we said, how do we take this and figure out how much time did it take us altogether? Well, so we said, look, this 2 here tells us that the number of levels in the tree, the number of levels of recursion is only going to be log of n to the base 2. This 3 tells us that at every level we are going to increase the number of nodes by a factor of 3. So we'll get 3 raised to the power of log n nodes at the bottom. And then we said, well, the fact that we take order n time, basically that says it's n time here and how much time at the next level, how much at the next, and so on. And then we realized, well, the maximum amount of time it takes us is at the leaves, and how many, so the running time is bounded by the number of leaves. Now we want to say, look, we figured this out sort of a la carte for this algorithm, but we're going to come across this over and over again when we do divide and conquer. So instead of figuring this out, sort of by hand, what we want to do is to say, look, whenever we write a recurrence like this, where we have a parameter like 2 here, 3 here, and n raised to the power of 1 here, right? So this particular thing, can we figure out what T of n should be? So in this case, we had T of n is n to the power of log 3 to the base 2. But what would it look like in general? And so that's what this theorem tells us. It says, suppose we are breaking up a problem of size n into A subproblems of size n over b. And then when we glue the solutions together, it takes us time n raised to the power of d. Then how much time does it take altogether for this algorithm? And the answer is given to us in closed form like this. It just tells us, we can read it off. So if you have a value of A, B, and D, like A equal to 5, B equal to 3, and D equal to 2, what's the answer? Well, you can just work it out, right? It just tells you what the answer is going to be. Okay?
Yeah, I got it. Thank you. So essentially what it is, it's just this is like a theorem that pertains to like the divide and conquer.
Yeah, absolutely. And it just tells you how to figure out the running time.
Okay. Then thank you so much for taking the time to explain that.
Oh, yeah, sure. Any more questions?
Yeah, hi, Professor. I was wondering how exactly the divide and conquer that you talked about, like you wrote the 4 points, right? There's like 1, 2, 3, and 0. Like when I was reading those, they seemed like they could apply in general just to like recursive algorithms. So I was wondering how divide and conquer is different from just the regular recursive approach to problem solving.
Okay. Okay. Well, we'll talk about it. By the way, when you ask a question, it would be nice if you actually, show your video so we can really have a discussion, right? But let's go back and let me make sure. Are these the four pieces that you meant?
Yeah,
Is that what you were asking about?
Yeah, the break into pieces, over them recursively, etc.
Okay, so divide and conquer is one of the most, it's one of the most common ways in which recursion is used. It's the most non-trivial way in which recursion is used. And so, in a certain sense, if you want to understand recursion, you have to understand divide and conquer. So you're putting your finger on something really important, which is, this is really an interesting, you've seen tail recursion already in some cases, right? And that's okay. There you're not doing divide and conquer often. That's fine. But when you really do use recursion in this very non-trivial way, often it's because you're doing divide and conquer. In fact, I'd have to think hard to think about a non-trivial, interesting case of divide and recursion, which doesn't come from some sort of divide and conquer strategy. Okay. Right.
Yeah. Okay.
Any more
I see.
questions?
So you're essentially saying that. Oh, just sorry. So to reiterate, you're saying that divide and conquer is the overall kind of problem-solving strategy, and recursion is kind of like a concrete example of when, like a way to implement a divide and conquer strategy.
Okay. Yeah. So it's built into divide and conquer, right? So when you do divide and conquer, you divide your problem into many pieces. Then you solve those pieces recursively. Right? So your recursion is completely built into divide and conquer. But also the most non-trivial recursive algorithms I can think of actually are doing divide and conquer. So they're almost synonymous, right? So, of course you can do recursion without doing divide and conquer, but I think the most interesting cases, the most non-trivial cases are actually doing divide and conquer. Okay? Any other questions?